Thank you, Si. Yes, apparently it's local custom not to have heavy theorems on Fridays, which is good. I hadn't been told that, but I'm not going to give you any massive proofs, but I'm going to talk about the three things mentioned in the title. Let me start off by talking about stratification. I think you all have a sheet in front of you that has definitions. So that's the one. That's the one. So have a look at the definition of the stratified formula. Now, stratification or stratifiability is a property of formulae. It's not a property of the objects that the formulae describe. So although if you look at that definition, you think this immediately suggests a many-sorted theory. It doesn't have to be. There are one-sorted theories which respect stratification disciplines. And as Si says, NF, which is my particular area of specialism, is one of the things, one of the theories that does. Now, stratification has its roots in simply the desire to avoid the paradoxes. If you have a stratifiability discipline on your comprehension scheme, so you only allow the set of all x such that whatever to exist if the whatever is stratified, then you're not going to get any trouble with a collection of sets that are not members of themselves. X a member of X or X not a member of X is not stratified, so you don't get the Russell paradox, and it deals quite effectively with with most of the other paradoxes. But there's it does look rather unnatural in some ways, but it's one of these things. I mean, it's a bit like learning to think with constructive logic. It starts off looking very weird, but actually, when you get used to it, you see that it has some very attractive features.
So
and you can learn.
It's a syntactic concept.
Absolutely,
yeah,
it's a syntactic concept.
It's not clear what the semantic meaning would be.
Well, this is what I was just about to get round to motivating it for. I think that something we all know that we don't talk about, well, we mostly don't talk about, is the endogenous strong typing of mathematics. Mathematics, as practiced, is actually a fairly strongly typed enterprise. Though we don't actually, the type system isn't particularly well defined and it's not enforced, but it's definitely there. And if you're a linguistically obsessed logician as I am, you notice this simply in the choice of letters that people use for different kinds of variables for different kinds of things. And this is all done, this is done informally, but it does, that discipline speaks to something in our language modules. And I think as I say, people don't go on about it a great deal, but I think it is an important part of the way in which we think about mathematics. Now, the novel thought I want to offer you is that stratifiability, which is something that appears purely in set theory, echoes and actually sits on top of, quite accurately, the endogenous typing distinction that we have in mathematics. And one particular example, maybe this is a bit recondite, but I'll try anyway. The Browley-Forty paradox. We all remember the Browley-Forty paradox. There's one analysis of this, which most set theorists haven't got time for this kind of thinking, but which is a shame because we should try and think in these ways. If you start off with the idea that the only thing in the world are sets, so you then have well-orderings of sets, and you have a notion of isomorphism between well-orderings. That leads you to a concept of ordinal. So you want to say two well-orderings partake of the same ordinal if they are isomorphic. And then you have a way, this gives you a way of talking about ordinals without actually talking about ordinals. You talk about sets or other well-orderings and never talk about, or never really committed to ordinals. Your variables that range over ordinals get replaced by variables that range over well-orderings, and your identity between ordinals simply becomes isomorphism between well-orderings. So sufficiently simple ordinal arithmetic can be seen as simply part of set theory in the sense that wherever you have alpha equals beta, you have well ordering A isomorphic to well ordering B. So that, one way of putting this, you could say these things are, your two well orderings are distinct as well orderings, but they're identical as ordinals. So the ordinals just are well orderings. So that gives you a virtual theory of ordinals. And if you like, you can then have what things called classifier functions, which enable you to.
It's so tempting to pick the canonical representatives of these classes. The ones
brutal, horrible
epsilon.
person.
Less than means epsilon.
Let me continue my pitch.
Okay.
Then
what's the advantage of not doing it?
Well, it gives you another analysis of Borelli-40. And Borelli-40 is the paradox of the order type of the collection of all ordinals.
You're Italian, you should know this.
Cesare Borelli-40.
You didn't know.
He was from Milan, it was Torino, I think.
And from Bologna.
Oh. Okay, so the narrative I've been suggesting to you gives you virtual ordinals. And if you work very hard at it, you can get sets of virtual ordinals, you can get well orderings of sets of virtual ordinals. And then you want to talk about isomorphism classes of these things, and these are doubly virtual ordinals. Now, if you do this sensitively, you can then find and then try and interpret it into set theory. It then turns out that the doubly virtual ordinals belong to a different type in the stratification sense from the singly virtual ordinals. So the stratification discipline echoes what arises naturally in the mathematical context when you think about ordinal. And this happens in other areas as well. But on the whole, the stratification disciplines don't cost anything in set theory because almost all mathematical notions, if you implement them naturally into set theory, go over to stratified formulae. It's a very striking fact. Ooh, come back. Now, there are a raft of nice theorems concerning stratified formulae. One of them, I've got a list of them here. Rieger-Bernays permutation models. Do we all know about Rieger-Bernays permutation models? Perhaps not under that name. Do you know how to prove the independence of the axiom of foundation from the other axioms of set theory? I think it should, yes. It's on the... Yes, the very first section under Rieger-Bernays permutations. If you have a structure for the language of set theory and a permutation of that structure, you can then equip that structure with a new, the carrier set, with a new epsilon relation. And there's a theorem that says that the new structure satisfies the same stratified formulae as the old structure. And you can, by these means, get new structures for which the truth value of some unstratified things is affected. Now, it's quite easy to show that stratified formulae are preserved by this operation. What is slightly less easy, but in fact is a sort of standard 1950s piece of model theory, that a formula is stratified if and only if the class of its models is preserved under this construction. But I think that's quite pretty. I mean, it suggests that, stratification isn't just a syntactic trick. It does have some kind of meaning. Another result, quite recent, I think this is the bottom of page 1. You start off with a model of ZF, possibly of ZFC, and you consider the symmetric group on V omega, right? So you have actually quite a small group here, and this group, okay, it acts on its permutations of the omega, so it's only moving stuff around here, but actually it has an action on the rest of the universe as well, okay? And in lots of ways. If I have a thing up here, I can either whack it with sigma in here, which will probably fix it, but I can also I can get sigma in here to act not just on this elements by sigma, but act on its members, or members of its members, or members of its members, and so on. So you want to say that a set up here is symmetric if for every sigma in the symmetric group on V omega, this thing is fixed by all but finitely many of those actions. Now that's actually quite a hard thing to grasp. But what it does mean is that anything that's actually in V omega is fixed. Because really what you're saying is, if I take, x is going to be fixed if there's some n such that if sigma acts on the nth time subset of x, it fixes x. And if you're actually in V omega, then you are of finite rank. And if you act more than n levels down where you're of rank n, then you're going to be fixed. So we say a set is symmetric if it is fixed by all but finitely many actions of a sigma down here. And then, of course, you can think about the class of hereditarily symmetric sets. Now, that's a bit of a mouthful. But it turns out this is actually quite a nice construction because it preserves all the stratified assertion. What you get, not so all the stratified things true in the original model. That's not quite true. But it does give you a model of the stratified fragment of ZF. If you started off with a model of ZF, then when you take the hereditary symmetric things, it's a model of all the stratified axioms of ZF, and it violates choice. Neil.
So do the unstratified instances of replacements break as well in this model?
Yes, they do, because you can't prove Mostrowski collapse lemma, which needs unstratified replacement. And one illustration of that is that, which is the next thing on my menu, is to say that there is an isomorphic embedding of the model you started with into the hereditarily symmetric sets. And because Mostrowski collapse doesn't work, you don't therefore get, the hereditarily symmetric is still a proper substructure of the model you started with. So, and the other nice thing, the isomorphism classes of accessible pointed graphs in the hereditarily symmetric sets is an isomorphic copy of what you started with. So why do I care about this? You start off with a model of ZF containing lots and lots of interesting unstratified information. You get a substructure of it in which you appear to have destroyed all the unstratified information. You've only preserved stratified information, but the unstratified information is all still there, encoded somehow in the stratified information that you have kept.
What is APG?
Pointed graph.
Oh.
Sorry, there are too many three-letter acronyms in this world, isn't there? Another piece of propaganda that I want to make for the stratified formulae is there's an axiom that Jean Corret, the French logician of the 1970s, had, which is that every set is the same size as a well-founded set. This is weaker than foundation. And every set is the same size as a well-founded set. So consider ZF with foundation weakened to this axiom of Corret's. This is a subsystem of ZF. It's also a subsystem of ZF plus the Forty-Honsel anti-foundation axiom. interestingly. It's not obvious that Forty-Honsel implies that every set is the same size as a well-founded set, but it does. And the interesting fact is that both these theories, ZF plus anti-foundation and ZF with full foundation, are extensions of ZF with Cloray's axiom, every set is the same size as a well-founded set, that are conservative for stratified formulae. Now,
you're trying to understand the content of stratifications. What you do, you understand what stratification?
I'm sort of attracted to the idea that everything you can do in a stratified way. Mm-hmm. That in some, and my categorist friends tell me that the category of sets according to ZF with foundation, the category of sets according to ZF plus AFA are equivalent. I'm not quite sure what that means, but it means something. I think it's trying to tell you that these two theories are sort of reporting on the same mathematics. Mm-hmm. And this suggests to me that, you know, since they agree on the stratified, on the stratified core, then maybe the stratified core is what's capturing the mathematics that they are both reporting on. I don't want to overdo it. I mean, but I think this is something that people should think about. Naturally, the stratified formulae have good syntactic behavior. There are a raft of results. Marcel Krabbe shows that if you take NF and you weaken it by dropping extensionality, because you can't do anything proof theory when you have extensionality, there's a cut elimination proof for NF minus extensionality, which trades heavily on the stratified nature of the theory. Also, the recent result of Jamie Gabai's, which I haven't been able to check, says that if you think of naive set theory with a set of rewrite rules for curly brackets, introduction and elimination, if you restrict it to stratified, you apply these rules only to stratified formulae, then the system is confluent. I haven't been able to reproduce his proof, but it's a believable result. Confluent. That means confluence. Okay, so I have a set of terms, and I have rules that enable me to rewrite them. And sometimes more than one rule is applicable. So I have a thing, I can rewrite it this way, or I can rewrite it this way. And a confluence result says, if you're in a situation where you can go in two directions, then you can always get back. There is a place that you can get to from both. Well, however far you've gone, you can always reach a common place. Right, but also in this connection, I want to talk a bit about synonymy. And we are never too old to learn. Or duster.
Or you want to erase?
That's better. I'm going to do that. No, don't worry. When I was young, nobody ever talked about synonymy. I think it was, well, some philosophers talked a bit about synonymy.
I have not heard the word until you come to Vienna.
Oh, come on.
Never heard the word synonymy. I was trying to figure out how to pronounce it. Now I know how to pronounce it.
It was all the
synonymous.
Synonymous.
It's synonymy.
Philosophers used to talk a lot about synonymy. I think Quine wrote about synonymy.
When you say used to, suggesting they don't anymore.
Well, maybe they do, but I haven't been reading what they've been writing. So.
Okay.
Synonymy. Okay, so I've given you two definitions of synonymy on this sheet here. So what's the idea behind this? You think two theories are synonymous if they're, the phrase I like to use, reporting on the same mathematics. And it might be that, one definition is that two theories are synonymous if there are interpretations from one into the other and the other into the one, which are mutually inverse.
Mm-hmm.
Another definition is, well, mutually inverse up to logical equivalence, shall we say. Or another is that any model of the one theory can be turned into a model of the other by some very, very simple-minded manipulation of the decorations of a model. So you think a model of the theory is a carrier set with decorations. If there's some very simple manipulation you can do to the decorations that gives you a model of the other theory, and these manipulations can be inverted, then you say the theories are synonymous. Some trivial examples of this. This thing keeps switching itself off. The theory of partial order and the theory of strict partial order. I don't know if you ever have to teach this stuff to young students. You have to explain to them, in some sense, these are really the same thing, really. I mean, you have this pre-mathematical phenomenon of an order relation, and you try and axiomatize it and try and formalize it. And it really doesn't matter whether you do it with this or with this, because they're mutually interpretable. So you do really have the feeling that there is, as it were, one noumenon out there that we have some kind of access to, and we have two different descriptions of it, and we know that really they're, in some sense, the same description. Boolean algebras and Boolean rings. You can turn a Boolean algebra into a Boolean ring and vice versa with the minimum of effort. But in both those cases, you have the feeling that there's, these are, as it were, in both cases, you have the feeling that the two theories are two attempts at describing the same mathematics. So it's not surprising that they should turn out to be synonymous in that sense. There are slightly more now there's some less trivial examples. The recent theorem of Tin-Lock Wong and Richard Kay, which I think is on this, yes, item 3 in the references. We all of us know somehow that the V omega is just the same as the natural numbers. And we probably know the isomorphism. Yes, you say, if x and y are natural numbers, you say x epsilon y if the xth bit of y is 1. Do we know this?
But I interpret all right, but isn't isomorphism a bit too...
Well, thereby hangs a tale. I think this.
Depends what relation you have on the numbers, right?
What Kay and Wong showed is that the theories, the pure arithmetic, and the set theory that is ZF minus infinity, plus the negation of infinity, plus transitive containment, these two theories are synonymous.
Okay.
And that's quite striking, even though we've sort of always known that these, these are the same thing, guys. To actually have it spelled out in that way is quite satisfying. Quite striking. It's something I may get round to saying something about later. Is that to get this synonymy, you need a sort of Beschränktheitsaxiom in the set theory, something that removes all the interesting parts. So,
what was transitive containment? What do you mean?
Sorry?
You said transitive containment.
Transitive containment. Every set has a transitive superset. You see, the reason you have to add that because in ZF you prove it by, you want a transitive superset of X, you consider X, some set of X, some set of X, and you construct the union of all those transitive closure, but you need replacement, you see, you need replacement and infinity. If you haven't got infinity, then you can't straightforwardly do it. But in a set theoretic context, I'm interested in the possibility of synonymy between unstratified set theories and stratified set theories. I think it was suggested by this result of mine about both ZF with foundation and ZF with anti-foundation being extensions of ZF with Koche's axiom that are conservative for stratified formulae. So you have the feeling that the unstratified stuff isn't actually doing anything. I'm also interested in synonymy between theories of well-founded sets and theories with anti-foundation acts, but also synonymy between theories of well-founded sets and theories with a universal set. Now, on your sheet, you have a definition. This is your second item, Church-Oswald constructions. Church was very interested in the possibility of a set theory with a universal set. That 1974 article of his is quite interesting, actually. He makes the point, and it's one worth making to oneself and also to one's students, that there's a huge difference between a theorem that says there's no universal set and the actual set theoretic paradoxes like the Russell class. The Russell class is a paradoxical object in the sense that if you want to prove that it doesn't exist, you can do this in first order predicate calculus. You don't need any set theoretic axioms at all. You don't need extensionality. You don't even need excluded middle. If you want to prove that there's no universal set, you have to do some set theory. So I think Church was very struck with this, that so the really big sets, the things like the universe, are not inherently pathological. The pathological sets are the intermediate ones, things that are neither fish nor fowl. He uses the word intermediate. And so he was interested in adding an axiom of complementation. So you can't just add an axiom of complementation, you have to modify separation as well, because you have to somehow find a way of thinking of sets as big or small, and then you have separation for small sets and not for big sets. And he exhibited a way of constructing models of these theories, and that's the one on your handout. Now, I've suspected for years that there's a synonymy result waiting to be proved, that this construction that Church gives is so cute and so elementary that one wants to say that, how do I put this? That it just isn't that ZF and Church's universal set theory are in some sense the same theory. They are, to use that phrase again, reporting on the same mathematics. Now here again, Church's construction can be tweaked in various ways, and Church himself tweaks it. I can't remember how many of the details he spells out, but I've spent some while writing out all the details for my own satisfaction. He can add Frege-style cardinal numbers for small sets. It's not very easy to add Frege-style natural cardinals for big sets, and you certainly can't add ordinals as equivalence classes for big ordinals. You can add them for small ordinals. So it's a fairly open-ended construction. And this, of course, obstructs the enterprise of showing that his theory is synonymous with ZF. However, if you add a sort of Beschränktheits axiom that says the only sets there are the old well-founded sets and their complements and surjective images of well-founded sets, then you can prove a synonymy result. And Tim Button has recently proved that as a side effect of doing something else. But I think, the fact that these synonymy results are available, I think is very suggestive. I mean, it's saying that, and I suppose I would say this being an NFist, I think it shows that there really isn't any mathematics at stake in the question of whether or not there is a universal set. It's not the kind of thing we should be worrying about. So, right, synonymy and Rieger-Bernays models. You start off with a model of some set theory. You start with a structure for the language of set theory, and you do a Rieger-Bernays construction. You get a new structure which satisfies the same stratified formulae. Can you get back to where you started? See, why does this matter? You see, if you can get back to where you started, then it means that the theory of the original model and the theory of the new model are synonymous in at least one of these senses, because you can turn a model for one into a model for the other and vice versa. And that will mean, I offer you the thought that that means that the stratified things about which they disagree are in some sense spurious. These don't actually, they're not actually doing anything. They don't mean anything. Now, there's a certain amount of tidying up to be done here, but it does seem fairly clear that certainly in an NF context, which is the context in which Rieger-Bernays models have been most studied, this process is reversible. You start off with a model of NF, jump into a permutation model, and then you can jump back and get back to where you were before. Slightly more difficult in ZF for technical reasons. One is that if you want to use Rieger-Bernays constructions in ZF, it makes a difference, certainly technically, whether or not the permutation you're using is supported by a set or not. If it moves a proper class of things, then it's slightly more difficult to work with. And the trouble is, whenever I study a permutation, I'm also interested in the other permutation that arises from that permutation by taking my first permutation and acting one level down. Sorry, that is not. So I have sigma. Sigma sends x to x. Then I have a new function we tend in the NF community we tend to call it j of sigma, jump of sigma, where jump of sigma of x equals the image of x in sigma. Now you see, sigma might only move a set of things, but j of sigma is always going to move a proper class of things. So that makes some of the calculations rather more difficult. But still, there are some synonymy results that have been obtained recently. One I proved a few years ago, even before I discovered this concept of synonymy. I didn't know I proved a synonymy result, which is take ZF plus foundation, or ZFC plus foundation, and relate that to ZF plus, there exists a Quine atom, okay, and x equals singleton of x, which of course violates foundation. There is an x which is equal to singleton of x such that for all y, if y has no minimal element, then x is in y. What does this mean? It means we've got a thing that's not, it's a violation of the axiom of foundation, but in some sense it's the only violation of the axiom of foundation. The only way any set can fail to be well-founded is by having this thing sitting inside it somewhere. And there's a permutation which will take you from this model, from a model of this to a model of this, which is actually the one that you may be familiar with, the thing that swaps the empty set with its singleton. And actually, any model of this contains a permutation which you can use to jump back to there. So I'm offering you the thought that really these are the same theory, right? So the question of whether or not there are Quine atoms is spurious in some sense. It's something we shouldn't be stressing about.
Very quick question about synonymy. this isn't talking about the permutation analysis of synonymy, but the one where you're looking at maps on the language. Is that sensitive to the meta theory you work in? So when you're working in something without foundation versus something with foundation, does it?
I think it must be. Yes, I think. Yeah, but and I'm not sure whether it's a question of foundation. Though, is whether how much arithmetic the theory has.
Right.
I would have thought that would be. Yeah.
Is that? I mean, maybe this can be left to the end. Is that then a slight worry that you have this notion of synonymy, but you want to argue that it's somehow telling you that different kinds of mathematics are the same, but then that notion itself is
sensitive to your set existence axioms.
It's very similar to a worry you get in the philosophy of set theory about this Hankins view that any first order model is just as good as any other of ZFC. But then you have to deal with the worry of what do you mean by ZFC, because you can have non-standard formulae floating.
I know. You could go crazy worrying about that stuff, couldn't you? Yeah, I think there is something to worry about that. I suppose. Hang on, if you make your theory stronger, isn't that going to mean you're going to be able to prove that more things are synonymous, aren't you?
Yeah, because it's an existential.
Yes. So what's that telling you? Very, very strong set theories. You're able to say, well, they're all these theories are the same. Lumpers. So that means God is a lumper, not a splitter. Right, so medium-term goals of this project. One of the goals I have is to understand a remark that Richard Kay made to me years ago, to the effect that there is no consistency proof for NF using these Church-Oswald constructions, which I take to mean that NF is not synonymous with any ZF-like theory. That I think is probably the case that we are going to find more synonymy results connecting ZF with foundation to ZF with anti-foundation. I think it is. I think it's just a matter of looking for them. Historically, people have been interested in mutual equiconsistency results and mutual interpretability results rather than actual synonymy results. But if Kay is right, and I think he's a clever bugger, Richard Kay. Mm-hmm. And he probably is right, then I think what that means that NF is not synonymous with ZF, that it really is reporting on something, is telling us about something different. So I look forward to somebody proving that every set theory is synonymous with its stratified fragment. A theorem along those lines. And I'm looking forward to somebody following Tim Button's lead and proving theorems about the synonymy of theories of well-founded sets with theories that have a universal set. I think we leave time for questions. I should probably stop there.
So you see, the only candidate we have for something not synonymous with ZF is NF. Other things are kind of universal set or.
I mean, isn't it still open whether ZF plus V equals L is synonymous with ZFC, isn't it? Well, it sounds extremely unlikely, but I don't think anybody's proved that they're not. Isn't that right?
Which sense of synonymous?
Either. I mean, they're clearly mutually interpretable, but I mean, I think.
Because you just.
Sorry?
Because L satisfies ZFC, and you can always find L within any number.
That's right. Yeah.
And so, what form of synonymy are you using?
Sorry?
What form of synonymy are you applying to this if it's not mutual interpretability?
Well, either, I think. Okay, take the one having the same model, having the same models. Is it the case that any model of ZFC can be turned into a model of ZF plus V equals L by replacing the epsilon of the model with something definable within the model? That sounds extremely unlikely, doesn't it? You give me a random model of ZFC. Can you define in that model? Can you define a relation in that model which turns such that when you decorate that model with that relation, you get a model of V equals L? Come on.
The global order.
Is that enough?
Oh, Jonathan is saying what? What? Why doesn't that work? So you just simplify jet L and V. Because they're both that in a definable way. Definable way.
Then you just put there the epsilon relation from L.
But you said any model of ZFC.
Yes. To be synonymous in that sense.
So, but then
we need
the global order. And so I think those are the ones that satisfy V equals I. Those are the ones where you can do that.
Oh.
The ones with global.
So does that mean that ZF plus V equals HOD is synonymous with ZF plus V equals L?
Yeah, I think in this sense, yes. This is a very generous notion of synonymy.
Well, that one's not generous at all. I think that one's actually quite strict.
Really? Well, I think of it as a mutual interpretability. Okay, yes, I see. There are more theorems.
More theorems.
Equals L, then not. What about constructive set theory? Is that a different story? Or I mean, I guess there are formal results which reduce it to classical set theory.
Yeah, but that's good because there are lots of mutual interpretability results, aren't there? I don't know what they. I mean, one thing that I noticed when I started writing this stuff out, I mean, this, you think of the synonymy of the theory of partial order and the theory of strict partial order.
Yeah.
You see, x less than or equal to y is equivalent to x less than y or x equals y, and x less than y is x less than or equal to y and x not equal to y. So you want these two to be logically equivalent, which of course they are classically, but they're not constructively. And I don't know whether that matters. I tried it out on a categorist theorem, and he spewed a lot of category theoretic jargon and said, so that's fine. So maybe it is.
Well, I think a set theorists are mostly interested in something called consistency strength of things, right? And this tends to be mutual interpretability in practice. And we have this dream, maybe you find it naive, that these strengths are sort of calibrated by cardinal axioms. Instead of C, Z of C plus con Z of C, you get to an inaccessible, you get to a measurable, and this is kind of religion there.
I think that's a
consistent theory should follow from the consistency of Z of C with some
plus some suitable,
or maybe Z of without AC plus some large cardinal.
Well, I think my take on it as an NFEist, you understand, I have a barrow to push in this regard. If you think that the universe is nailed down at one end and sort of flies off and over there, high speed, then what's going to if you have something that is extremely improbable, the nearest example of it is going to be a long way away. And if your set theoretic world has a direction, then that means it's going to be a big thing. It's not going to be over there or over here, or you know, it's going to be a long way over there. So the fact that all your strong axioms turn out to be large cardinal axioms, I think that's an artifact of the axiom schema foundation. Really. But I mean, I don't know how serious I am. I just say that in order to annoy ZFists. But
well, I mean,
it's always worth a try.
Your point is maybe NF is consistent, but none of those reasons, right? It's just it's an outlier. It's on the side, right? But you're not going to derive this consistency from large cardinal axiom.
Well, I think. Well, I hope and expect that Randall's consistency proof for NF is good.
Oh, what's the status?
The status is that nobody disbelieves it. And several people believe it. Including also other people
what
who...
about Tom Forster?
I haven't mastered the details. My feeling is the techniques he's using, there's no reason why they shouldn't work. You know, because cranks for years have been coming up with consistency proofs for NF, and there's always been a very, you can see this thing isn't going to work for completely elementary reasons. And there's nothing like that with Randall's proof. There's no reason why it shouldn't work. It's a very complex construction, and there are lots of annoying details. And one of the troubles is that Randall, he's always reconfiguring the annoying fiddly bits because he thinks there's a nicer way of presenting the construction. And so you have this moving target.
Oh, it sounds like Brexit.
No, no. I think it's.
What's the proof relative to?
It all goes on inside ZF. You can construct the whole thing inside it. I think if you worked very hard, you could probably do it relative to, I don't know, Zermelo plus the existence of Beth Omega, something like that. NF is not a particularly strong theory. So yes, I think he's probably done it, but I'm not.
Yeah.
I think it would be nice to get someone to do a computer verification of it, actually. I mean, I think if that were a project, then it would force Randall to write out one version of the tweaked proof that somebody could actually verify. No, I think I'm very hopeful. I think there's no reason to suppose that the claimed result is false, and there's no reason to suppose that the alleged proof is faulty in any particular way. So, but, fingers.
So has anyone ever attempted the proof in the other direction? I mean, to extract just a little bit of consistency from the consistency of NF?
Yes, I did that in my PhD thesis. Yes, several people have tried that in the 1970s. What you can do, you can try and develop a theory of well-founded sets in NF, but that's quite difficult because it's still an open question whether NF proves the existence of infinite well-founded sets. It proves the existence of infinite sets, but we don't know that it proves the existence of infinite well-founded sets. So that's not really the way to do it. Another thing you can do is look at the isomorphism classes of well-founded extensional relations, the set pictures, well-founded set pictures in NF. And of course, those equivalence classes in NF, they're actually sets, so they're very easy to deal with. And Roland Ignon did that. That was his PhD thesis, 1974. And you get Mack, McLaren set theory, but you should get a bit more than that. And the other thing you can do, and somebody ought to do this properly, is look at reasoning inside the ordinals of NF. You should do, I don't know, what would you call it? You can consider the recursive construction of L over the ordinals using the rudimentary functions. But instead of using that to construct actual sets, you use it to construct a binary relation on the ordinals. So that, as it were, you create the sets, then you copy back the membership relation onto the ordinals. And that way you should get a relative consistency proof of some well-founded theory plus V equals L from NF, but nobody's ever sat down and written out the details.
What was Quine aiming for? Simply a way out of the paradoxes?
I think the story is actually quite simple. I think Quine, he just thought that type theory had this unnecessary duplication, what Randall calls the hall of mirrors effect. That you have the empty set at every level. Come on, guys, one empty set is surely enough. Mm-hmm. So you take typical ambiguity seriously. You just say you prove the same things at every type. So why not just say there's only one type, and then and then you as it were you export the stratification discipline from the model into the syntax. I think it's this book. Quine wasn't interested in any of the propaganda that I'm giving you.
This fancy name is called New Foundations. Was that Quine's name for it? Or
yep.
other...
It's the article.
Well,
the article was called New Foundations for Mathematical Logic.
There.
Well, I think Quine was a very good propagandist. I think.
Do you think it's tied up with his views on ontology of properties, that properties should be just understood as extensions, and then you need
it might be
the universal set, for instance, because x equals x is clearly a legitimate property.
It might be. I don't know. I mean, this is I suppose there's a race of Quine scholars now. I mean, I wonder to what extent Quine's views on logic are connected to his views on philosophy of science. And one suspects not much, but you may be right. I don't know. It's worth a thought.
And a couple of questions. One is, so this difference between the Russell paradox and the paradox of Cantor's paradox.
Yes.
So there's this debate that goes on quite a bit as to whether the set theoretic paradoxes and the paradoxes of truth, for example, the liar, are somehow the same thing. Do you think that this is maybe the distinction between the set theoretic paradoxes and the semantic paradoxes is not quite the right distinction to be making, because Russell might go in with the semantic paradoxes, whereas Cantor and possibly Varela Forte, I don't know where that would fit.
I mean, it's Ramsey's terminology, isn't it? The difference between the semantic paradoxes.
I don't know where it at first appears. You just hear it a lot.
You hear it a lot.
Argued about
Yeah. Yeah, I suppose. I mean, Russell paradox, the Russell paradox, and its congeners. The collection of sets that aren't members of any member of themselves, and so on. I mean, I think it is worth banging on about the fact that you can prove the non-existence of these things in first-order predicate calculus. You don't need any semantic apparatus. You don't need any logical apparatus beyond that. And I think that's important, and it's worth emphasizing. But I say for me, the difference is between those paradoxes that you can just do in a purely logical way, and those that need some extra apparatus. And whether that apparatus is semantic or set theoretic, I'm not sure. I mean, anything other than the purely logical paradoxes can be really do your head in, really. I mean,
yeah. The second questions were, I mean, maybe they're a bit speculative, kind of technical things, but one was, have you looked at, you mentioned this result about equivalence of categories for theories with foundation and without. Have you tried doing this for category of NF sets
Well, Garth, the category of NF sets is under active investigation by, but part of the problem is that if you want to investigate the category of NF sets, you need someone who understands categorical set theory, and you also need somebody who understands NF. And the intersection of these classes is extremely, well, it's probably empty, actually, really, truth be told. But I have an article with two students of mine that is going through, it's got lost in somewhere through the process of being accepted by the JSL. But yes, I mean, this question of what the category of sets looks like according to NF is an interesting question, and there are people looking at it. Yeah.
And the second kind of technical question was whether I mean, some of the stuff you said about typing was very similar to what the permutative type theory people say. They say things like, look, typing is everywhere in mathematics, so we should incorporate that into our foundations. Are there general relationships between stratified set theory and, let's just say, Martinez type theory or something?
I think yes, there are. I think there's a huge amount to be said about that, and I'm trying to write a book about it. But of course, we're all trying. We're all trying to write books. But I think yes, I think you're right. I mean that there are connections, and they do need to be. The endogenous strong typing of mathematics is something that we need to not just sort of assume and feel comfortable about it. I think we need to examine it and see what the fallout is for foundations of maths. Yeah.
I think it's important to distinguish between two different set theories if they're really just different ways of talking about the same method.
Well, I'd like to get straight whether they really are just two different ways. Yeah, I mean, Marco Forti used to say that it's purely historical. Marco Forti was one of the authors of the Antifoundation axiom, Forti and Hansel, two North Italians. And I remember Marco saying to me years ago that it's purely historical accident that when set theory got axiomatized, that it was with foundation, not anti-foundation. There's just, that's just. It could have gone
He's
the
the
other way.
only living person who would say such a thing.
No, I think you can make a good case for it, actually.
Read Boulos.
Well, I mean, Neuromanov is very sympathetic to it in the early 20th century, but once Zermelo starts writes his famous paper.
Yeah, but you see, all the philosophers of mathematics, they've been given a fait accompli. They're told by the mathematicians, here's the actual foundation. And so they spin these wonderful epic yarns about how mathematics is resting eternally on the carapace of a giant empty set. It's just, if they'd been given a different story to tell, they would have told, they'd have told it differently. I mean, and I think if it does turn out that ZF with foundation and ZF with anti-foundation are synonymous, not only that they have the same stratified theorems, but that they're actually synonymous, then I think all this stuff about the endless propaganda about the cumulative hierarchy can all be binned.
Watch this space.
I like your controversiality.
Well,
In Kyo's book, there's a nice discussion about foundation and how it's completely irrelevant to normal mathematics.
But he didn't know about anti-foundation.
No,
He didn't know about that.
Sorry, who's this?
Cunan's set theory.
Oh.
He just says, well, we can go to the inner model where everything's well-founded, and so we don't really need to worry about the foundation.
And he almost never talks about philosophy, so it must mean it's important. It's very important.
Okay, so what does the fact that it's an inner model prove?
Well, you take the well-founded set, so you have it.
Yeah, but you want it to be an elementary for something, don't
You
you?
just wanted to say that if you take foundation out, that theory still has the same strength. It's equally consistent.
Oh, okay. Yes.
And he proves it in the book, I guess.
Yeah.
So he says, from now on, all sets are well-founded because they might as well be.
Hey, just useful, so let's do it. Come on. Doesn't really change anything. It's just a nice.
But he didn't say B equals L, did he? He didn't say, well, I could build it on all sets are constructible, not just well-founded.
Maybe.
But he also says that hard is a very boring model. There's nothing we can prove about it.
About how?
Also true.
All right, well, thank you very much, Thomas. For